Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Fbise from Department of Physics. This is lecture 17. Before moving towards lecture 17, we make a review of previous lecture 16. In previous lecture 16, we discussed the conductance and conductivity, effect of temperature on resistance, temperature coefficient of resistance, and variation of resistivity with temperature. Today we are going to discuss why won't variable resistors, thermistor and its applications. First of all, we come to why won't variable resistors. High stability and high accuracy resistors are always wire wound resistors. You can see here in the given figure, here is a rod and over it there is a conducting wire in the form of loops. It is wound, and such type of resistor is known as a variable resistor. The wire which is wrapped is made up of nickel chromium. It is used because of its very small temperature coefficient of resistance. What is temperature coefficient of resistance? Temperature coefficient of resistance means change in the resistance of a resistor due to change in temperature. They are enclosed in an insulating cover. These resistors can operate safely at higher temperature than carbon type resistors. Wire wound variable resistors can be used in two ways. It may be used as a rheostat, it may be used as a divider, potential divider. First of all, we come to the use of wire wound resistor as a rheostat. The figure is giving you a rheostat. This is an insulating cylinder. Over it, there is a conducting wire which is wrapped, giving you two free ends. And these two free ends are behaving as two terminals of the device known as rheostat. Here is a third terminal, that is sliding contact. This contact, because it is clear from its name, sliding contact, this could be moved over it. So the third terminal, unlike A and B terminals are fixed. These are the free ends of the conducting wire which are always fixed. But the third terminal, the third contact, which is known as a sliding contact, is always movable. When it moves over it, this gives you the variation in the length of the conducting wire. To use the variable resistor as a current control device, one of the two fixed terminals, say A, and the sliding terminal C, are inserted in the circuit. So definitely when we use the third contact, that is the sliding contact, this changes the length of the conducting wire. And in the previous lecture, we discussed that resistance of a resistor is directly proportional to the length of a conductor. Smaller the length, more would be the resistance, and vice versa. So when resistance changes, so definitely there is a change in the current, because we all know R and I, what type of relationship is there? If R, that is the resistance, is more, then the current which is passing through the conductor, it would be less, and vice versa. In this way, the resistance of the wire between A and the sliding contact C is used. If the sliding contact is shifted away from the terminal A, the length and hence the resistance included in the circuit increases. You can see here as we are moving. When the sliding contact C is shifted towards A, then the length of the wire decreases. This decreases the resistance of the conducting wire. Adjusting the resistance in the circuit controls the current in the circuit. This is the making of a simple rheostat. Enameled copper wire is wound around cylinder. Washer is used as a slider, and effective length of wire changes as we slide, resulting in variable resistance. Okay, now we come to this activity where we have to make a rheostat. For this purpose, we are going to use an enameled wire, and this enameled copper wire of 34 gauge, you can see how it is wrapped over this insulating cylinder. And when it is wrapped, and we have to remove the coating along a line, because I told you it is enameled wire. So in order to make it naked, so that the contacts are very clear and very sharp, we have to make it naked. And in this way, we have to find the resistance at different points. And you can see when we connect it with the avometer, then as we are moving here, the resistance changes, and this in turn changes the current. Okay, now how to connect it in a circuit? For this purpose, we have to make the terminals. You can see that there are two free ends of the enameled copper wire, and this is the first end. And how we are introducing here screws, and the screws are giving you the contacts, the fixed contacts. This is A, and now the other free end of the bare naked copper wire, and this gives you the contact B. And now we are going to insert the sliding contact, which is in the form of this washer. As the washer is moved over it like this, you can see how we are moving this washer, which is connected with the terminals A and B, and the third terminal is a sliding contact. And now we are connecting this rheostat with the terminals of the battery. All right, so this is a bulb. It glows when current I is maximum. The bulb, it glows. So what does it mean? When resistance is less, then it glows. All right, try with copper wire with different diameter wire, so the resistance, it changes, and vice versa, the current also changes. Now we come to the second use of wire wound resistor as a potential divider. A potential divider provides a convenient way of getting a variable potential difference from a fixed potential difference. So in the circuit diagram, definitely we are going to use a battery. A battery is providing a constant potential difference, and from that constant potential difference, we are going to get a different or variable potential difference. This could be done with the help of a device which is known as a potential divider. With the help of a battery, a potential difference V is applied across the ends A and B of the resistor. Let R be the resistance of the wire AB. The current I which is passing through it from Ohm's law is given by I is equal to V over R. Okay. If R, B, C, for this purpose, let me consider. If RBC is the resistance of the portion of the wire BC, and the current passing through BC is I. For this, let me consider here the circuit diagram. In the circuit diagram, this is a battery which is providing a constant potential difference V to the circuit. And this is the direction where the current I is flowing through the circuit, and A B is giving you the length of the conducting wire, and let me consider, instead of considering the whole length AB, let now we consider the BC portion of the length AB of the wire. For this purpose we consider C point. Here is C point, and when we consider C point, then what happens? This is giving you BC portion of the wire AB. So RBC, what does it mean? RBC is giving you the resistance of BC length of the wire. Alright, then the potential difference between B and C point is given by VBC is equal to I into BC. So VBC is equal to, instead of I from Ohm's law, we write here V by R into RBC. So VBC is equal to RBC over R into V. Depending on the position of the sliding contact C, the value of the fraction RBC over R can be varied between minimum to maximum, that is from 0 to 1. So it means where we move C maybe towards A or towards B, in doing so the length of the conducting wire, it changes, which in turn changes the resistance, and when resistance changes, then this fraction RBC over R produces a change in the voltage, which is given by VBC. So in this way, by making use of potential divider, instead of considering the potential for the whole length of the wire AB, if we want to find the potential at a limited portion of the wire, we can make use of this formula which we have derived now. When the sliding contact C is moving towards B, the length and hence the resistance RBC of the portion of the wire decreases. So when length decreases, then what happens? Thus VBC also decreases. On the other hand, when the sliding contact C is moving towards A, the length and hence the resistance RBC of the portion of the wire increases. So it means the length of the wire, it may be increased, it may be decreased by controlling the sliding contact C. When C is moving towards A or it is moving towards B, in doing so the length of the wire changes, which in turn changes the resistance, and finally there is a change in VBC. All right. Thermistor, as it is clear, it is combination of two words, therm, and therm means temperature, and resistor. So it means it is that device, it is that type of resistor whose resistance vary with the variation in the temperature. A resistor made of semiconductors having resistance that varies rapidly and predictably with temperature is known as thermistor. So basically thermistors are semiconductors because their resistance changes with change in the temperature. A thermistor, short for thermal resistor, is a heat sensitive device usually made of a semiconductor material whose resistance changes rapidly with a change in temperature. A thermistor has the following important properties. The resistance of thermistor changes very rapidly with change of temperature. The temperature coefficient of a thermistor is very high. The temperature coefficient of a thermistor can be both positive and negative. Positive and negative means PTC and TC. PTC means positive temperature coefficient. Those thermistors whose resistance increases with rise in temperature, and TC, negative temperature coefficient, deals with those thermistors whose resistance decreases with rise in temperature. Thermistors are made from semiconductor oxides of iron, nickel, and cobalt. They are generally in the form of discs or rods. You can see here in the given figure a cylindrical shape and rod, bead, and this side the symbolic representation of a thermistor when it is connected in the circuit diagram. You can see here a pair of platinum leads. These are attached at the two ends for the electrical connections. When we connect it in the circuit, we use such legs. The arrangement is enclosed in a very small glass bulb and sealed. It is then sealed. Okay, you can see here two thermistors, NTC and PTC. Such type of thermistors whose resistance depends on temperature. Thermistor is a device which is mostly used for temperature measurement. Their resistance changes with change in temperature. All right, this is PTC. This is a symbol, how it is used in the circuit diagram. This is when we plot a graph, resistance versus temperature, then variation of resistance with variation in temperature is shown in the given graph. Such type of curve comes. NTC, it is made up of nickel, cobalt, manganese, metallic oxides. These are used, baked at high temperature. They are available in various shapes like bead, rod, and discs. They have small size, so they can be easily fitted where the temperature need to be. You can see here in the circuit diagram, battery, ammeter. This is the thermistor. When it is used in the circuit, definitely temperature rises, and that rise in temperature shows the change in the resistance and vice versa. Where thermistors are used, what are the applications of thermistors? Thermistors with negative temperature coefficient of resistance may be used to safeguard against current surges in a circuit where this could be harmful. For example, in a circuit where the heaters of the radiator valves are in series. You can see here in the given circuit diagram, we are having a resistor R, thermistor capital T, and a heater. These are all connected in series with the terminals of the battery. Applications of thermistor. Thermistor capital T is included in the circuit. When the supply voltage is switched on, the thermistor has a high resistance at first because it is cold. It thus limits the current to a moderate value. As it warms up, the thermistor resistance drops appreciably and an increased current then flows through the heaters. Modern appliances, communication tools, and accessories like mobile phones, computers, LCDs, displays, CPUs, rechargeable batteries, and medical and patient monitoring devices are all equipped with thermistors, so they can be used continuously without fear of overheating and appliance damage. A thermistor with a negative temperature coefficient, that is NTC, can be used to issue an alarm for excessive temperature of winding of motors, transformers, and generators. When the temperature of windings is low, the thermistor is cool and its resistance is high. Therefore, only a small current flows through the thermistor. When the temperature of winding is high, the thermistor is hot and its resistance is low. Therefore, only a large current flows in the coil to close the contact. All right. We come to thermistors again. A thermistor is a heat sensitive device. This is the conclusion of our discussion. They convert heat energy into electrical energy, that is into electrical current, by controlling the resistance. By changing the resistance, this in turn changes the electric current. All right. What happens then? Most thermistors have negative temperature coefficient of resistance. This we have discussed it earlier, that most of the thermistors, they have negative temperature coefficient. Thermistors are made up by heating under high pressure semiconductor ceramic made from mixture of metallic oxides of manganese, nickel, cobalt, copper, iron, etc. These are pressed into desired shape and then baked at high temperature. Like in the figure, having different shapes. Thermistors with high negative temperature coefficient are very accurate for measuring low temperature near 10 Kelvin, which is equivalent to minus 263 degree Celsius. In the end, Marie Curie, a famous physicist, its quote, "You cannot hope to build a better world without improving the individuals. To that end, each of us must work for our own improvement." Thank you.